Okay, guys. Good morning. Let's get started. So, just a quick note about the last sessions. I remember we talked about momentum-based methods for a stochastic gradient descent, and we talked about Nestrov's momentum. And later on, I mentioned about RMS prop and atom. So eventually, you're going to learn about those more in neural networks in a week or so. I mean, as I talked about in the last session, they're pretty easy to implement, just another variant of momentum-based, stochastic gradient descent. So those two are eventually will be considered in your, in your contents of the course. All right. So before we start neural networks, let's just wrap up a generalization case for logistic regression. So what if we have, instead of a binary class, like class true or false, what if we have multiple classes? For the case that we have a binary logistic regression, the class could be 0 or 1. But if you have more than classes that we define them with C value, so C could be any numbers greater or equal than 2, so you'll end up having a multi-class logistic regression, right? And we talked about it today, and we talked about a new function which is called Softmax, which is pretty easy to implement. It's very intuitive, and you're going to, or you might have seen it a lot in all the neural network libraries like TensorFlow or other things that they're dealing with multiple classes of either regression or classification. All right. So suppose you have y as a set of numbers 1, 2 up to c, be the set of possible labels for your classes. So by this class, I mean, so instead of the original version of logistic regression that you had, the weights here, the x's vector, and the weights vector, and you would apply the sigmoid function, and you would go for either 1 or -1 as your y's, so class y. So instead of this paradigm, suppose you have multiple classes here. So how you going to define which value corresponds to each class, right? So eventually one of them is a true class. Suppose this one was the correct label. So we call it I. But for the rest, which were not correct, so let's say we call them L equal to I, talking about these three. Okay, so let's see how we're going to generalize this to a multi-class. And that's, I mean, it's pretty easy, but yeah, we're going to formalize it today. So in this case, our C was 3 because it starts 0, 1, 2, and 3, which represents for all the 4 classes. Assume the classes as like cat, dog, I don't know, chicken, and others. So you have multiple images, you want to classify them or find a regression line. So think about it also as this way. So you have a set of data minus this. Maybe. So you want to find lines to divide these 4 classes. So think about it this way. All right. So now let W1, W2 up to WC be the weights vector for each of those classes. So each of those classes are definitely have vectors. So the probability of I, which is the true class, given xn, is going to be calculated this way. Let me just, if you finish taking note of those, let me just erase them. It's going to be visible. All right. The probability you need to calculate in order to find the correct label for your class, the final class. Previous layers. Suppose this was I. So the probability of I is going to calculate this way. It's going to be because you have a logistic regression, you're going to use a sigmoid function to compute that and assume I as your data specific true class, which was the correct class, true label. And this is just a normalization with respect to the other classes that existed in a set of classes you had. So it just you calculate a value, a probability value for that, and it's going to be like 124. So the probability of I given xn. Okay, so that's for the only true labeled class. Suppose the C was true for that class. So you have to normalize it to all of the probabilities, all of the P's. And this summation comes because of that. So all the classes, class 0, 1, 2, 3, okay? And given this normalization, you're going to find a number, and this number would be from 0 to 1. Obviously, because you normalize it to all the probabilities, right? And that's normally the output of a softmax. Yeah.
So can I just do 1, 2, and 3? Or so that the sum goes from j equals 1 to 1?
Oh yeah, because here we have started from 1. Yeah. In my examples, I started from 0. Yeah. So suppose you have 4 classes. So you basically divide the probability found by all the classes, and then this will give you a number from 0 to 1, and you simply pick up the maximum likelihood, right? And so you see that it's pretty intuitive. So the rest of the class is just formalizing this. So the whole process, finding this, and dividing these two, and picking the maximum number, all three together is going to be called softmax function. So it's no rocket science, you know. Softmax function is pretty intuitive. So they put together all these 3 things, and then they call it softmax function. And that's why you see at the very latest, the final layer of most of the CNNs or RNNs or DNNs, specifically in CNN, it is visually, can be observed. So you have a softmax function in order to find the correct label that was estimated. And then we can compute the gradients between the estimated label and the correct label. All right. So let's talk about softmax function. So suppose you had C classes, right? Another very naive approach would be just to solve a multi-class classification with C different class of binary, classification, right? Instead of having one that, so I'm talking about the last layer here, you had like 4 C's. Instead of having one that does this, multiclass. You could have have 4 of these with binary, right? So this or that, right? Instead of doing on the left approach, you could have done naively on the right approach, but this is not efficient because it doesn't make sense to, suppose you have 100 classes, you cannot just do this and it doesn't make sense. So the job of softmax is compute and normalize the last layer's weight using the activation function you had, like in this case was sigmoid, and find a maximum probability in order to match the class, right? Let me just get rid of this again. Yeah, so instead of training C classes and just finding a maximum, which was not efficient, you can just use a softmax function. So these are the previous layers and this is the last layer. You can implement the softmax function here that does the job for you, as I explained in the previous slide. So let's see how we're going to formalize this. So this is applies. So predict, can an example X belongs to the class I in C for which the probability that has true label applies is the highest, which was this, and instead they use a softmax function, right? It's readable. So this is actually instead. Instead we're using a softmax. So yeah, note. Okay. So softmax function generally force the output layer to be a discrete probability distribution for C classes. Even for regressions, you can when you have some probabilities at the end, when you normalize it to the summation of for all classes, then you can pick up and you can sort them by the maximum number. Then you can pick up which class was estimated first and which was next, and so on and so forth. So in order to calculate the loss function, as I mentioned, let y of n be I, and that I is the true label. Well, actually, so label should be better like this. Okay, so suppose you have 4 classes. So one of them is the correct label, right? We call that I or y of n. So the loss function we had in logistic regression was computed as En of omega minus the log of p hat I given xn, right? And omega was a set of weights for each of the classes, right? So each of them are a vector of weights. for class 1 up to class C, right? So now we compute the gradients for each of those WIs for the true class in the next slide. So, as I mentioned, it will be equal to the output of the sigmoid function of that true class on top. That's the yn, true class, divided by normalization of summation of all the classes. So this is like all classes. So we basically normalize it to find a number from 0 to 1. Okay, so if you solve this, so you're gonna have this. You can get rid of the denominator from the log, bring it outside. So you're gonna have this one left, and then if you calculate the gradient of this, only xn survives. Then you have to take care of that. So from here, if you go on, so if you here you go on, you see that this comes here outside the formula, and then you're going to have this multiply 1 over this dot product of your xn, and then finally, so this would be for true class. This is one formula. For the other classes, the case that L is not I, you're going to have this. So instead of I, you have L here. L. Still, you have the summation to normalize the weight to that. Okay. All right. So this is also called, if you check the literature or if you Google sometimes, you can find that it's called also, instead of softmax logistic regression, as a softmax regression, or multinomial regression as well. So there are different names that they call it. So a visual difference as a generalization of a binary logistic regression to a multi-class with a softmax would be like this. So the softmax is actually doing will be placed here. So it has this, it has the normalization, and you want to find the maximum value. So these three things together is going to be the softmax function. And then the output, you're going to calculate it. So as an example, suppose you have, here in this case, C was 3, you had 3 classes if you start from 1, or C was 2 if you start from 0. Right? You have 3 classes. So the weights are coming here, the inputs, and then you had the weights. So here you calculated 3 numbers, right? 125, 70, and then 0.12, right? So this was the output of the sigmoid function, right? That was the output of this. E to the raise of x, t, w, that was the y, right? So the output of this, suppose in these 3 classes, you found these 3 numbers, right? Then you're going to go for you have to normalize this, you have to find the summation of each. So it's as if you go 125 divided by 125, 70 plus 0.12, 70 divided by 125, 70 plus, or at 7, 12, and then 12 divided by the same number, like 25, 70. So the final values would be, just compute it. So it would be like 64. Or that's 64 for the first class. $35 for this. And less than 1 almost for that. So the interesting point about the softmax function is, finally, if you take a look at the weights here that has been calculated at the very end, these probabilities, if you sum these 3, it's going to be always equal to 1, depending the classes. So in a real world application, when you are using like ResNet with ImageNet classes, which you have 1,000 classes as the output, right? Because ImageNet it has 1,000 classes. So this matrix would have 1,000 rows, and so the softmax function, the way you do the classification finally is finding the maximum number from these probabilities, and that's going to be your estimated class. So in this case, our first one had the highest number, That's why we can say that that's the estimated class, right? And also another point, suppose you have like, I don't know, 20, 100, in the case of ImageNet you had 1,000 of them. So this is called also the output of a CNN. In this way it would call top 1. Right? It was top 1 prediction. If you were classifying it, if you sorting it by maximum number, so if you sort the top 3 one, it would be like top 3 accuracy or top 5 accuracy. And that's why you see all these numbers for recent CNNs that, for instance, ResNet has a top 1 accuracy around 80, I don't know, 4% for ImageNet and 95, 96% top 5. So you might see in your next tutorials some examples about this. So one of the common approaches in order to compute this with multiple classes is to use one-hot encoding scheme, right? Does anyone know about it? One-hot encoding? Who doesn't know? Okay. So suppose it's a pretty intuitive approach. So suppose you have 4 classes. Okay. So instead of going for this number, if you have to present the classes just with a binary value, like 0 and 1, so the one-hot encoder gives you this option. So for class 1, class 2, 3, and 4. If you use one-hot encoding. So the class 1 would be 0, 0, 1. The class 2 would be 0, 1, 0. The class 3 would be 1, 0, 0. Well, actually, we used more numbers than needed. We could have just presented it with 2 numbers. So for classes, you could just use two values, like 0, 0, 0, 1, 1, 0, and 1, 1, right? So if you go for a one-hot encoding scheme, you can present it this way. Let's see what happened here. Let me clear this out. Yeah. So your first class would be here, 0, 0. The second one would be, the third one would be this one, and the fourth one would be just 0 all, right? This was one way to define the 4 classes just with binary values using one-hot encoder, right? And starting from this point, so this vector represents the first class, 1, 0, 0. This vector represents the second class. This one, the third one, and the fourth one. There's no need that you can define it whichever you like, right? You have like more classes, you can define it whichever you like. And starting from this, you could compute your matrix of x's and then maybe biases later on and the weights. And then given this scheme, finally, your softmax output would be having 3 numbers for each class, right? Like 39, 28, 56, like, I don't know, whatever, 27, and 3 numbers for this. In that occasion, you would choose the highest value in each row. Suppose this was the highest value, the max. And that would be this weight that you choose here, right? So in your examples, when you might do an exercise, you can consider using one of the encoding scheme for multiple classes.
Sorry, just where it says output, what's that symbol above the word output?
Where?
Like in the red, it says
Oh, here.
output, it's going to imply.
This one?
Yeah.
That was a sigmoid function.
Oh, it's like,
Yeah. So the output of the sigmoid function would become this, right?
okay.
And then you have to normalize the values, and then you pick the highest one, right? These 3 steps is called Softmax function. So that's why I put it here. 1, 2, 3. Yeah, it's kind of messy, but hope you got the idea. All right. So now let's see how we're going to generalize this to applying a stochastic gradient descent later on. So 100 encoding scheme was clear. Does anyone have any questions about it? Okay. All right. So for the updates of a stochastic gradient descent, suppose you have k iteration just as before, and your matrix of weights, which we call it omega k, has wk1, wk2 up to wkc, and c was the number of classes you had. So suppose these are the correct estimate that you chose for your true label I, yn equal to I, right? And as you know already, so in a stochastic gradient descent, we sample n from a uniform distribution, so 1 up to n. So we need to compute the gradient of En for WL. So this notation is actually, so the gradient of the En of WL is actually the gradient of En at the point of En when En was having this vector of W, WK1, WK2, up to WK, the last one, right? It's just a form of combining these two together. So you have this. Okay. And just like before, for a stochastic gradient descent, you need to calculate the next step given the gradients of the current step. Thus, your final value would be wk plus 1. The next update of L is equal to the current W of L minus the epsilon, which was the step size of this value that you compute. So it's going to be the same as the binary class, just a generalization when you have L and L is for those classes, right? It's going to be the same. Okay. So I guess we're almost done, and in your next tutorial you might see some examples of multi-class logistic regression. So starting from next week, we're gonna go for neural networks, followed by the forward propagation and then back prop, and then before your midterm, we're gonna have a couple of sessions about CNNs, and then you're gonna have your midterm. Okay, any questions? Right, then I'll conclude the session now. See you on Monday, guys.